Here we go. Got any questions about this shout, please? Otherwise, new lesson. Newton's method. All right, we're going to talk about finding roots by linearization. We're going to talk about how, again, to approximate a root function at a particular value. And we're going to talk about how this thing can behave badly. Okay? All right, people who want to start writing this can start writing this if you want. Okay, all the time we find ourselves needing to solve equations. Okay, what does that mean? We're trying to find the values of variables that satisfy the equation. Okay? That's harder than just evaluating a formula, okay? We're trying to solve an equation. But as I've said before, in very few cases can you do that exactly analytically, okay? So when you have polynomials that are degree 5 or higher, or if you have transcendental equations, it's usually impossible, or at best very painful, to solve those things exactly. So what we need are numerical algorithms, okay? Something that a computer could do to approximate the solutions of equations. Notice that any equation in a single variable x can be rewritten as something that looks like this. Okay, and we saw that before when we talked about bisection method. You can rewrite them like that. So what are we really looking for? We're looking for a numerical algorithm, okay, that will approximately find solutions of these kinds of things. So we're really looking for zeros or roots of functions, okay? So what we want to talk about is root finding algorithms. Root finding algorithms. Okay, we've seen one before. It's called bisection. We'll do a new and more sophisticated one now. Okay, there are many of these. Okay, one example is the bisection algorithm. And the new one we're going to talk about is Newton's method. Okay, what did we need for bisection to work? We needed continuity. Now we know about a special new thing. We're going to use differentiability. Okay? Bisection method relied on the intermediate value theorem. Here we're going to be using linearizations. What did we evaluate for bisection? We evaluated the sign, okay, plus or minus, of f at various points. Okay? Now we're going to be using the values of f and its derivative at various points. In bisection, we started with an interval on which we knew the root must lie, and we refined it, narrowed it down. What we're going to do here, let's see, is we're going to start with an initial guess, one number of where the root must be, and we're going to refine that. So instead of refining an interval, we refine a number, an approximation. Okay? So now that we know about the derivative, we can come up with a more sophisticated, more impressive, faster algorithm at the expense that sometimes it can behave badly and fail, where the bisection could not. Okay? Very good. Let's talk about this for 6 minutes. Newton's method, named after somebody or other. Also called Newton-Raphson, with contributions by Simpson. So like with a lot of stuff in math, the name that's on it isn't necessarily the guy who did the most work on it or the best work on it, okay? But it's called Newton's method or Newton-Raphson. Okay, and it's ludicrously popular. You'll see this a lot if you deal with numerical things. Okay, so what are we looking for? Again, we're looking for solutions of this. We're looking for zeros of a function, roots of a function, okay? Or x-intercepts of the graph of the function. So let's draw a very complicated function. Y equals f of x Okay, and this is the baby we're looking for. Okay, the root r. Okay, we start with an initial guess. We start with an initial guess, x sub 1 close to r. X sub 1. Okay, we start with initial guess, x sub 1 close to r, of where we think the root should be. Okay. And then we're talking about linearizations all the time. Let's use them. Okay? We construct the tangent at that point. Okay? What's the equation of that tangent? We've talked about this before. It's this. Okay, it's just the equation of linearization, right, essentially? And what are we going to say? Again, what's x1? It's our initial guess. Initial guess. What's the idea here? If we're close to r, okay, then this tangent should be a reasonable approximation of that curve close to here, okay? So this tangent should cut the x-axis close to where the actual function does, okay? So again, we're approximating the curve by the tangent, and we're approximating the x-intercept of the curve by the x-intercept of the tangent, okay? So we're saying, well, the true root, r, should be close to this thing, to the x-intercept of the tangent. We'll call that x2, okay? This is our new approximation. What's the point? Lines are easy. Lines are easy to find the intercepts of, unlike f. Lord knows what that looks like, okay? So, how do we find the x-intercept? We set y equals 0, and set x equal to x2, and let's find x2. 0 minus f at x1 equals derivative at x1, x2 minus x1. Rearrange that to solve for x2, and you get this. x2 is equal to, I will write it here. x2 is equal to x1, again, just by rearranging that and solving for x2. x1 minus f at x1 over the derivative at x1. So that gives us the x-intercept of the tangent. And the idea is that that should be closer to the true root than our initial guess was. Okay? Okay. And if you want, what are we really doing here? We're solving. Okay, if you want to think about it this way, think about it this way. What did we do? We're solving the linearization centered at x1 being equal to 0. I don't think that clarifies anything, but if you want to think about it that way, the linearization centered at x1 equaling 0, hitting the x-axis at x2. Notice that this thing falls to pieces if the derivative down here is 0. You can't divide by 0. That's a problem, and we'll talk about that again later. Okay, and my final thing I'm going to say. Okay, now, we got a better approximation. Why stop there? Go again. Okay? From here, build a tangent. Find the x-intercept of that tangent. Make that your new approximation, x sub 3. And keep doing that over and over and over again. That's what that thing tells you. Okay? Start with x sub 1, then keep updating. Get x sub 2, x sub 3, and so on. Okay? That's why it's called iterative. Like the bisection algorithm. You started with an initial guess, and then you made it better and better and better by doing the same thing over and over and over again to the approximations you got each round. Okay? And you stop when you get to the desired precision. Okay? And we'll do an example next time where we show what that looks like. Okay? That's it, everybody. Have a beautiful weekend. Thank you. Quiet, people. Okay, we started Newton's method last time. to find the roots of functions, or to try to approximately find the roots of functions. So we talked about this, and I said we'd do an example. So let's do an example. Here's what we're going to try to do. Very hard shot. Approximate the fifth root of 3. Fifth root of 3. Okay. Now you could ask, can we do a linear approximation like we did last time, right? Last time we had this thing, right? And we used linear approximation. So we centered at 9. Why? Because 9 was close to 9.3, and because square root 9 was nice. We linearized, and we used that approximation to approximate square root 9.3. You say, can we do it this time? Not really. Or at least not well. Okay? So the only fifth powers, or the closest fifth powers to 3, let's put this, the fifth powers on either side of 3 are 1 and 32. Okay? If we center at 1, we'll get that approximation. If we center at 32 and use the linear approximation, we'll get that approximation. Okay? The trouble is that 3 is too far away from both 1 and 32, and so the approximations we get are garbage. Okay? We don't even get 2 significant digits out of it. Okay? So again, approximation, true value, approximation, true value. And again, as you can see, not even 2 significant digits are right, so that's useless. We can't use that. Okay, you could try using higher order or higher degree Taylor polynomials, but we don't talk about that. So what else could you do? Incidentally, I should bring this up. I said it's too far away. How far is too far? Those of you who did the Taylor polynomial / linearization project would have seen that you can graph stuff, and you can see within what interval you'll get a decent approximation. And there are also error bounds that you can put on things, and how far you can get and get a decent approximation depends on what you consider to be a decent approximation and the second derivative of this function. You don't need to know any of that. Okay, but it is possible to estimate how far away you can get without getting into trouble. Okay, so we need another method. So what we'll do is, we'll frame this question as a root finding question. Frame as root finding. Okay, why? Because then we can use Newton's method, right? We like to do this. We like to change our questions to something that we've seen before, and we can solve using the tools we have. Okie dokie. So, we want x, we want to find x that satisfies x equals the fifth root of 3. Okay? That's the same as saying x to the power 5 is equal to 3. And that's the same as saying x to the 5 minus 3 is equal to 0. Hey, look, we're looking for the roots of that polynomial. Okay? So, let fx equal x to the 5 minus 3. And let's look for the zeros of f. Or the zero of f. Okay? Alrighty. That's what that function looks like. And we're going to look for its zero, or its root. Note, this thing is continuous and differentiable everywhere, so we won't have trouble with either bisection or IVT or Newton. So that's good. So always check that the thing fits the requirements you need for the method you're going to use. And here we go. So for Newton's method, you need an initial guess. Okay, so you need to know roughly where you think the root is. So what's our initial guess? You can just blindly guess and hope that takes you to the right place, or you can be slightly more intelligent. So you could note, as we did for IVT and bisection, those kinds of things, you could note this. F at 1 is equal to what? 1 to the 5 minus 3 minus 2. F at 2 is equal to what? 2 to the 5 minus 3, 32 minus 3 minus 29. I mean, sorry, 29. Okay? And you'll remember from intermediate value theorem that if we have something continuous and we go from negative to positive, then at some point we have to cross 0. Okay? And on the graph you can obviously see this. Right? At 1 you're under the x-axis, at 2 you're above the x-axis, at some point you have to cross. Okay. So by IBT, there must be a root on the interval 1, 2. Okay. That shouldn't be too surprising, either from the graph or from the fact that we just talked about the fifth powers on either side of 3 are 1 and 32. That's exactly what that's saying. Okay, so we know this thing has to have a solution between 1 and 2. So you could just be slightly stupid and just say, okay, let's make our initial guess somewhere in the middle there, 1.5. So let's make our initial guess 1.5. Okay? Okay, what else do we need for Newton's method? We need the derivative of f. Okay. The derivative of f is 5x to the 4 by the power rule. Questions? Yes, ma'am.
Why did you choose 1 and 2 again?
A hunch. Basically, you have to find out the one's negative, one's positive.
Right.
So you can look for something that does that, and the best you can do is the best you can do. Does that make sense?
Sorry, I just didn't know.
You can also look at the picture, yeah.
Yeah, I just saw the picture and I was like, okay.
But if you're looking at the picture, you wouldn't really say 1.5. You'd say something like that, right?
Yeah.
Yeah, basically you go from minus to plus, and just pick two numbers to do that, and IBT will tell you there's a 0 there, and then you can pick the midpoint if you want, or something like that. And I'll get to later how that's a slightly dumb way of doing it, but it works. Okay, so for Newton we also need the derivative of f, and that's the derivative. Good? Okay. And now if you'll remember this thing, that formula there, that update formula. So our update formula is going to be the next approximation is the current approximation minus the value of the function at the current approximation over the derivative at the current approximation. Okay. I'll just sub in. X to the 5 minus 3, x to the 5 minus 3, 5x to the 4, 5x to the 4. Okay, nothing weird yet, right? You can either look at the graph and figure out an initial guess, or just start guessing numbers, or using some kind of logic, or use bisection to get close to come up with an initial guess. You need the derivative for Newton, and that's the update formula for Newton. Okay, so if you just remember that, or you find it using the linearization each time, that's cool. And you'll get this. Okay, so the next approximation you get from the previous approximation through that. Okie dokie. Okay. I think I've written it in full there. Okay, so we had our initial guess, and we want our next one. So our next approximation is given by this thing, yeah? It's given by x1 minus x1 to the 5 minus 3, 5x1 to the 4. And my guess is you won't be writing all of this the same way as I do. Grand. Just do something that's clear. Okay, our first guess was 1.5. So you just do 1.5 minus 1.5 to the 5 minus 3 over 5 times 1.5 to the 4. Right, and you'll get that number. Approximately 1.3185185. Okay? Does that make sense? I just used the formula we had. good. Okay. So there we go. What did we do? We were at 1.5. We constructed a tangent. We found its x-intercept, and look, that got us closer to the root, which is exactly what Newton should do. Okay? And that's our new approximation there. 1.31 whatever. Okay? So we got closer. And what's the idea? It's an iterative procedure. Let's do it again. Okay, so we do exactly the same thing again. Okay? To get the next approximation. 1.25, whatever. What did we do? We took the previous approximation, constructed the tangent, found its x-intercept, and look, we're getting even closer to the true root. Yes, sir?
How do you know when you have the right answer?
I'll tell you in a second. Yeah, I'll tell you. How do you get the, how are you done, right? Is that what you're asking? Yeah, I'll get to that in a second. Thank you. Good. And again, this is the kind of thing a computer loves to do, right? It's brainless, it's repetitive, it's great for a computer. Okay? Or a guy making figures in his lunch. And then just one more. X to the 4 you get from x to the 3 by doing the same thing again. And you notice we're getting closer and closer and closer. Okay? We are converging, and remember what we mean when we say sequences converge. The sequence of approximations is converging to the true root, which is there. Okay? We're getting closer and closer and closer and closer. Okay. So just keep doing that. We are converging to the true root. And when Newton does converge, it converges to a root. Okay. This is to answer your question. Okay, so suppose someone had said, they wouldn't just say approximate this, okay? They would say approximate that to 7 decimal places, okay? Or 7 significant figures. Okay, so again, these are the approximations you get, and you could keep going forever, okay? Now, how do we go about this? So again, suppose we said we want this thing accurate to 7 significant figures. See what's changing from one approximation to the next, okay? So between these two approximations, the 1 is the same and nothing more. Between these two approximations, the 1 is the same and nothing more. Okay, between these two guys, this has gone wrong again, hasn't it? He keeps doing this to me. Okay, I'll have to tell you, don't trust the red. Okay, so between this approximation and this approximation, the first two are right. 1.2 match, and then everything else is different. I apologize, the colors keep going wonky on me. Okay, 1.2 is good, and everything else changes. Okay, between this guy and this guy, 1.245 is the same, and then everything else is different. Okay, between this guy and this guy, you can do the same matching game. Okay, so see between successive approximations which digits match. Okay, and that kind of suggests to you which digits have settled. Okay, and when the right number of digits have settled, then you can stop. Is that fair? Okay. So basically, looking for digits settling, and I'm going to fix this a second time now. I don't know what's going on with the colors. Check between successive approximations which digits match. When you have enough, you can stop. I'll write that now. Check matching digits between successive approximations Stop when you have enough. Okay, and either us or your needs will tell you what is enough. Okay. And in this case, I said, suppose we want to approximate it accurate to 7 significant digits. Yes, ma'am.
Why, what's the purpose of doing this if we get the same answer as plugging 3 root 5 into our calculator?
Great question.
Yeah.
Yeah, the question could be, how's your calculator doing it? Which I think is not quite this. But a computer could do it this way, right? So if you had to figure out how to do this from scratch, this is the kind of thing maybe that you'd be doing, or something cleverer. And I'll do an example tonight about, something else. Whenever you want to solve stuff in general, you could use this, right? Yeah. So for problems more general than just finding the root, this works. And by the root, I mean like the fifth root of 3 is a dumb thing to try to find this way manually each time. You just use your calculator. For other stuff, you could also use Newton, and it's possibly more useful. Okay? All right, so again, if I said get this thing accurate to 7 significant digits, what would you do? You'd wait until, let's say, 8 significant digits had settled, and then you could be confident that your first 7 here are giving you the right answer, and then you could write that down, and you'd be done. Okay? Check matching digits, and I'll fix the colors again tonight. Okay? And I think, how much is enough in this case? X to the 5 will be enough. Okay? So if you look here, up to there is good, and up to there, I think we've got what? 8 significant digits matching between those two guys, okay? And so if you just round, then you'll get 7 good significant digits. Okay, so in this case, x to the 5 is sufficient. Sorry, x sub 5 is sufficient. Okay? Just check for matching digits, see how long it takes for the thing to settle. And I'm guessing the numbers are again wrong here. Brilliant. Oh, one more thing I want to tell you, which won't be clear again because the colors are wonky. In Newton's method, roughly speaking, you double the number of good significant digits after each iteration, okay? So, let's say, what do we got here? Here we have 2 good significant digits, and the next one will have roughly 4, the next one will have roughly 8, and so on. So each iteration gives you twice as many good significant digits, roughly speaking, as the last one did. Bisection doesn't do that, okay? Bisection on each iteration won't even add 1 good significant digit. It might add 1 good significant digit every 3 iterations, okay? The lesson is that bisection is much slower than Newton, okay? That's what you need to know. Okay, so roughly speaking, in general, typically, the bisection method is slower to converge than Newton is, okay? Which is why, in some sense, Newton is better. Okay, again, I apologize for the colors. The starting guess matters, okay? So I said 1.5 might be a slightly dumb guess, okay? Because if you looked at the graph, you can see that the root was closer to 1.2 than it was to 1.5. So if you'd seen that sketch, or you'd sketched it yourself, then you would have said, okay, let's start at 1.2. And if you start at 1.2, you converge slightly more quickly, okay? By which I mean you get to a reasonable approximation in slightly fewer steps, okay? But the thing is fast as hell anyway, so it barely matters, okay? Another way to think about it is that this is a lot closer to 0 than this is, so you'd expect your root to be closer to 1 than to 2. So you might guess 1.2 rather than 1.5, and you might get to your answer slightly faster. Okay? Initial guesses matter. And I'll just say this again. Typically, Newton converges more quickly than bisection. Okay, again, bisection roughly adds 1 good significant digit every 3 or 4 iterations. Newton roughly doubles the number of good significant digits in each iteration. Okay, Newton gets to where you want to go faster. Okay? Okay. Notice at each iteration, what do we have to calculate? We have to calculate the value of the function and the value of its derivative. And you might go, well, how would a computer calculate the value of the derivative? Either you'd have to tell it what the derivative is, as well as the function, or it would do it symbolically, kind of the way you would, or it would have to use an approximation of the derivative. And those of you who did that discrete difference quotient project would know that you can approximate derivatives, okay? Using those kinds of things, or more sophisticated methods, okay? Just a note on how computers would have to work, okay? So computers would have to approximate the derivative or figure it out somehow to be able to do this. Okay. And I was going to say this, and then you asked me, in tutorial I'll do an example that you couldn't figure out just by punching into your calculator 5th root of 3. Okay? Something slightly more adventurous than that will do. Okay? Newton's method applies broadly to find roots of functions. Okay? Any questions? Comments? All right. Again, be able to do this, understand the broad strokes of it. All right, behaving badly. Again, don't go nuts on the details of what I'm about to say. Try to pick up some general ideas. Okay, Newton is more sophisticated than bisection. Okay, look, it converges more rapidly. Okay, and if you didn't understand what I was saying about the number of digits, let me know. But Newton converges more rapidly than bisection, typically. But the trouble is Newton can fail. Okay, whereas bisection, once you get started, can't fail. It will just keep going closer and closer to the root. Okay, but Newton can fail. So let's see a bunch of ways that it can fail. One, you could leave the domain. Okay, so suppose that was your initial guess. You made your tangent, you found its x-intercept, and now what the hell do you do? You're not even in the domain anymore. Okay, trouble. Okay, you can try another initial guess, or use another method. Okay? Here's another one. If the derivative at whatever guess you're at is 0, you've got a problem. Okay? If you remember the Newton update formula, I'm convinced either me or someone else is going to get the derivative and the value mixed up. Make sure you get those in the right order. Notice in there, if you've got a 0 here, you're in trouble. Okay? You can't divide by 0, so you're stuck. Okay? And that's all this is saying. Okay? If at your approximation you get a 0 derivative, your tangent is just going to be horizontal. It's never going to hit the x-axis unless you were there to begin with, in which case you're already done. Okay? And if you're in a situation like this, you can't go on. There's nothing to do, so pick another initial guess or pick another method. Okay? So again, you can't divide by 0, or the tangent never crosses the x-axis. Similarly, if the derivative is approximately 0, okay, so if the curve is a bit flat or shallow where you are, that might throw your approximation far away, okay? So if instead of being flat, this thing looks like this, it might throw you far away, and it might throw you out of domain, it might throw you to a far away root, it might mean that you wind up further away from the root than you were in the first place. Bad things can happen. Okay. Let's look at green. If I start here, nice things happen. I converge to probably the root that I was looking for. If I start at red, that thing happens. I get thrown away to some other root, and then I converge to that. If I start at blue, I get thrown away to another root still, and I converge to that. Okay? It matters where you start. Okay? These two are pretty close together as initial guesses. Okay? But they converge to different roots, and neither of them is the closest one. Okay? It matters where you start. And if you have multiple roots you're trying to find, you need multiple initial guesses. Okay? One for each root, and they had better be good initial guesses. So it can be tricky to use this method. Okay? So if you pick a bad initial guess, you might wind up at a different root than the one you care about. You might wind up not converging at all. Crazy stuff can happen. This is a really sick pathological example. If you start here, the tangent will take you here. Okay? Make a tangent. It'll bring you back. Well, that stinks, doesn't it? Okay? You never get any closer. You're sure as hell not converging. You just keep bouncing back and forth between those two approximations. Okay? It stinks. Okay, and here's something more extreme than that. You can show yourself really easily, all right, using this thing, that with that function, the cube root function, no matter where you start, apart from the actual answer, no matter where you start, the next approximation will be on the other side of the 0 and twice as far away. And then twice as far away, and twice as far away. And things just keep getting worse and worse. You don't converge. You just get further and further away from the true root. Okay, it sucks. Okay? So Newton's method just doesn't work for this kind of function. Okay, so the lesson is, this thing is sophisticated, it's fast, but you've got to be careful. Okay? That's it for Newton. Any questions? Man.
I don't understand when we're supposed to use Newton's and when we're not supposed to. Like, how would we know not to use it for that example?
In this example?
Yeah.
You wouldn't. As far as I'm concerned, you would, yeah, if you tried to, you would see bad things happening.
Okay.
like on a test, we're not gonna do that to you. I don't think that's gonna happen to you, if that's what you mean. Okay, yeah. Haha, you know, you did, no, that's sick. I mean, conceivably, someone could give you that and say what's going wrong or something like that. But I mean, to just say, all right, here's a thing, try to solve it using whatever method, and if you go wrong, haha, that's not test material, right? Yeah. In practice, you'd see the properties of the function. Again, if you tried to write that out for that thing, you'd see very, very easily that it's screwed. You're just getting further and further away. You've got a problem. Okay. Or if you try it for a few iterations, you'll just see your numbers are getting bigger, and you're just getting further and further away from any number, and that's not good. Okay. All right. Yeah, don't panic about details on this. Questions?